Hi everyone, it's my great pleasure to introduce Anna Gusakova today from University of Bochum. She's gonna tell us how to estimate mean distances. Anna, please.
Many thanks for the introduction and many thanks for the invitation to give a talk on this seminar. So I'm very happy to do it. And as it was just mentioned, I will be talking about sharp inequalities for the mean distance of random points in convex bodies. This is a joint work with Jill Bonnet, Christoph Terry from Ruhr University Bochum, and with Dmitry Zaporozhets from St. Petersburg. And I will start with some motivation and historical remarks, and I will start from a bit far away from the famous Sylvester's question, because I would like to give the full motivation and also somehow the deep review, historical review of the problem. So let K be two-dimensional compact convex set. So I will start with 2 dimensions. That's how the problem was originally formulated. So for example, this is our body K. And I take 4 points which are uniformly distributed in K and independent, so x1 to x4. And then I would like to consider the convex hull of those points here. So this is the smallest convex set which contains all of them. For example, like on this picture, I have 4 points, and this is my convex hull here. And I define P for K. It is a probability that this convex hull, which formed by these 4 points, is actually a triangle. So as you can see on this picture, it's obviously not a triangle, but if one of points is lying in convex hull of other 3, then we have a triangle. And Sylvester asked this question in 1864. It's also called 4 points problem. He asked whether we can evaluate this probability. And when he was asking this question, it seemed to be not that complicated. I mean, that's very easy to understand the problem. That's very easy to formulate it, but it's actually to evaluate it for any K. It's extremely hard problem. But actually a lot of work has been done since then, and people have been investigating this probabilities very intensively. And in this table, I summarized for which bodies K it's actually possible to calculate this probability precisely. And so that can be triangle, for example, square or regular pentagon, hexagon, octagon, and at the end we have circle here. And I will not give the full references for these results, but if you are interested, you can, for example, take a look on this work of FIFA, the historical development of Sylvester's 4-point problem. And in this table, the values are ordered in such a way that they increase starting from here, and then we go in this direction. So that's why also Sylvester said something like, yeah, well, maybe we can at least find the minimum and maximum value which these probabilities can attain, and for which body, for which convex body this probability is attained, and probably its lower bound is a circle and upper bound is triangle. So, and this is already like the first problem where some function of convex body is asked to be maximized and minimized on the set of convex bodies. And this question was fully answered by Blaschke in the 1970s. And yeah, he proved exactly what was claimed, that this probability is between 1/3 and 35 divided by 12 p square. And yeah, but this is not the kind of functionals I would like to consider in this talk, so it's not interesting for me, at least not today, but it has a connection with the functional which is of interest for me. So what we want to achieve at the end. And let's see why this connection works here. Okay, so as I already said briefly, that it seems like this convex hull is triangle when one of the points is lying in convex hull of other 3. So I can write like this as a probability that one of points one of points x1 to x4 is in convex hull of other. And since all my points are the same, like they're independent and identically distributed, I can, without loss of generality, say, okay, let it be x4, which is line in convex hull of x1 to x3. And then I can say this is then 4 multiplied by the probability that x4 belongs to the convex hull of x1, x2, and x3. Okay, and then I can write this probability in such a form that I take expectation with respect to x1, x2, x3, and then I take probability with respect to x4, and again that I want this x4 to be in the convex hull of these points x1, x2, x3. Now in this probability, it's probability with respect to x4, so x1, x2, x3 are fixed in this point. That's why this probability I can, of course, just write down. So this is the area of this triangle, convex hull of x1, x2, x3. And divided by the area of the body K. And then we are already there, so I just move expectation here upstairs because area is of course independent of anything. So, and I get that my functional is in fact 4 multiplied by this functional here, or this probability. And this is exactly the kind of functionals I would like to consider today. And yeah, well, since we have already the upper and lower bound for this probability, we can also directly follows from Blaschke's results that we have also upper and lower bound for this functional. So, and it's also important to have something like area of K here down, because I would like my functional to be affine invariant. And that's exactly what happens if I normalize this averaged area of this triangle with the area of my body, because if I apply any affine transformation here now, then this is the full dimensional triangle, the 2-dimensional triangle. So its area will scale like the determinant of affine transformation, and the same will do the area of K. So it's invariant under affine transformation. So I will write affine invariant. And it's also the reason why here stays in this table not only circle, but in fact I can take any ellipse here, because any ellipse is affine image of the circle. So that's why for any ellipse the value is exactly the same. And now I can discuss what is actually equality cases here. So equality cases here is, as it is expected and it's proven, equality holds if and only if K is ellipse. And equality here holds if and only if K triangle. So, and then in 2 dimensions, the problem is completely solved. Now I would like to formulate a small question. So it's like preliminary question, let's say in 2 dimensions and simple situation, and big question I will formulate a bit later. So small question. Here in this situation, which I just discussed, we have 3 points and the convex hull is full dimensional triangle. What happens if I now take just 2 points? So I take points x1 and x2, x1 and x2, and I take the convex hull. The convex hull is just a line segment, and that's not a full dimensional object anymore. And of course, it doesn't make sense to measure its area, but we can measure still length of this segment. So I can ask what is the average length of this segment. And again, that of course depends on the size of the body, and I don't want it to be so much dependent on the size of the body. But I can't just divide by the area of the body, because under affine transformations, it's not anymore true that this line will or this length will scale like a determinant of affine transformations. That's not the case. And moreover, it's one-dimensional object, so I have to normalize it differently. And the question is, what would be the correct normalization in this case? And the intuition says, if we are working with one-dimensional objects, then we have to normalize by some one-dimensional characteristic of the body. And in this case, I would suggest to normalize it by perimeter of K. And then again, the question is, what would be the maximal and minimal values this functional now can attain on the set of convex bodies? And now small spoiler. So spoiler, because I will formulate more general and the main result later, but this is what already will follow from this main result. In this simple case, it will follow that this value actually is placed between 7/60 and 10/60. And inequality signs are strict here. So we will never, there is no two-dimensional convex body K for which these values will be achieved. So, but anyway. And that is like small, like I say, spoiler. And now, before I move to formulating the problem itself, my problem, I would like still to say a few words about what happens in general dimension with this Vestas question. Of course, there can be, the generalization can be considered in this high dimensions. So we again take a convex body, and instead of triangle, the high dimensional analog of triangle is a simplex. So in order to form a simplex, I need d+1 points, which again uniformly distributed in K and are independent. And as before, I would like to consider the convex hull. And this is d-dimensional simplex. Then I take the volume of this simplex and expectation. And again, I would like to normalize it in a way so that it's affine invariant, and that's again, the normalization is volume of K. And the question is again the same, what would be the maximal and minimal values this functional can attain? And in high dimensions, its situation is more complicated. And if the minimal value is the classical result of Gromer, which he proved in 1973, it's also known like Blaschke-Gromer inequality. And the body for which the minimum is achieved is d-dimensional unit ball. So that's like in two-dimensional case. And again, equality here holds if and only if K is an ellipsoid. And the value, this f of BD, is also calculated. It's calculated by Kinman in 1969, and this is given here, so it's quite precise. So we know exactly what is the minimal value this functional can achieve. And with the maximal value, that's a much more complicated question, and it's an open and famous problem, which is called simplex conjecture. So it is a conjecture, it's not solved by now, but conjecture says that Fk should be smaller or equal than f of Td, where Td is a regular simplex or d-dimensional. Regular simplex. Yeah, in fact, by affine invariance, I can take any simplex here, not necessarily regular, but so this is a conjecture. Yeah, and it stays open by now, and some other nice conjectures like hyperplane conjecture also follows from this one. How one can generalize the situation more, or what also was considered, they can also consider not only expectation, but we can consider higher moments. Say r bigger or equals than 1. So I put r here, and my functional now also depends on r. And this generalization was considered again by Grömer in the same article, basically 73. And again, the minimizes ball. So ball is this universal minimizer somehow in this kind of problems. And we also can consider, we can take, say, n points, which is bigger than or equal than d plus 1. So instead of here d plus 1, I take n points. But again, the object I obtain here is not simplex anymore, it's some polytope, but that's a full dimensional polytope. And it's again, the question was considered by Grömer 1 year later. And he also again proved that this is a minimizer. So it's only about minimizers, and usually minimizes the ball. So and now finally I can move to our problem. So as I said, there were already attempts to consider more points in d plus 1, but I actually would like to consider this situation when there are less than d plus 1 points, so k plus 1 point. Then my object convex follows those points, it becomes lower dimensional, and at least I lose this nice affine invariance here, and so the problem became more delicate. I will not say much more complicated, because here there is a simplex conjecture at least, but it becomes more delicate. So, and in this talk, I would like to consider a specific situation when I have just 2 points, x1 and x2. So, as always, we have some convex body K. We have now 2 points uniformly distributed in K independent, and we consider their convex hull, so this line segment joining them. And my functional, which I would like to consider, this is expectation of the length of this segment. So, or I can write it down in the avoiding this probability signs. I can also write it down as an integral. So it's divided by volume of K. And this functional was considered already. So that's also a separate question to evaluate this average distance between 2 points in a body, in a convex body. And a bit more things are known in 2 dimensions. So in 2 dimensions, we can consider ball, we can consider regular triangle or rectangle or regular hexagon. And formulas are known and explicit, but quite complicated. So I would say so at least. And in 3 dimensions, one can also consider a unit cube. And for unit cube, this kind of integrals is actually known like a box integral. And it's also known that in 4 dimensions and further, this box integral does not have a closed form. So it's not possible to even write it down explicitly anymore. And if we move further in arbitrary dimensions, then basically the only case one can treat is ball due to its nice symmetries. And it's also possible to treat the situation when we have a d-dimensional ellipsoid with this given semi-axis. And then we have this formula. But I again would like to point out that this kind of integral, it's an elliptic integral, and so you can't evaluate it further. That's it. that's a form, the best form you can expect. So, and that's why situation is getting a bit more delicate, and you can already see like for ball we have some number, and for ellipsoid we have something multiplied by some functional depending on ellipsoid. And that's why, in order to study this again, maximizing, minimizing problem, I would like to somehow normalize this functional again, to come back to the situation when I can, for example, treat ball and ellipsoid like in the same manner. So when it doesn't matter whether we consider ball or ellipsoid, some kind of a fine invariance. And so I call it like normalization. How do I need to normalize my object in order to study the problem? And there were already few attempts to do it. So the first attempt was to normalize it by volume in power 1 over d. The idea is also, it's clear where it comes from. If we scale our body by some number t, or just consider scaling in all directions by t, then the length of the interval scales like t and the volume like t in power d. So that's like an idea. And then if we scale like this, then the lower bound has been obtained, but no upper bound. And this lower bound, or this equality case, equality here holds if and only if k is a ball. So not for ellipsoid, only for ball. And another attempt was to normalize it by some one-dimensional characteristic of the body, for example, diameter, and this upper bound was obtained. But we claim that both these normalizations are not ideal and they're actually not correct. And the correct normalization is different. And in order to talk about this, I would like to introduce two new, a bit more notation. So first of all, if I have some interval in RD, I will always denote like this the length of this interval. And one important one-dimensional characteristic of a convex body is so-called mean width, which can be considered like average projection of this body K onto the uniform line uniformly chosen. Can be written in this form. So where PU is an orthogonal projection operator from RD to the linear span of this unit vector U. U is vector from the unit sphere. So like on this picture, for example. So here this projection of K will be this segment. And mean width is already good, but usually people consider normalized mean width, the so-called first intrinsic volume. And the reason for this, if I now, for example, take an interval, so my body K is just an interval or segment, and the interval, and then I increase the dimension of this space RD where my interval is living, then this mean width will go to 0, and that's bad. But with this normalization, it will always stay the same, and for the interval, this first intrinsic volume or normalized mean width is always the length of the interval. And that's why it's good, because with this normalization, it does not, so this parameter depends only on body K, it does not depend on the dimension of the space where we are living. And for my future purpose, I will, yeah. There was a question? Okay, maybe not. So for this, for my future purpose, I will denote this constant by alpha d. So to just shorten the notation a bit. And my claim that correct normalization and is exactly this first intrinsic volume of this body K. So I would like to normalize my functional delta of K by this value. And finally, I formulate the question. So we would like to find minimizer, something not correct, minimizer and maximizer of this fraction on the set of convex bodies. And so our main result is this theorem, and it's actually very surprising. I mean, I will now write it down, and I already say that result is surprising because usually what you expect, knowing all the story about Sylvester problem and other estimates, you usually expect that minimizes ball. It's not the case in this situation. So, and for any convex body K, so we have that this value here is placed between 1/3. And here I have some constant depending on D, which I don't remember by heart. So this is 3D plus 1 divided by 2D plus 1. In here, 2D plus 1. And I will denote this by CD. So, and I already mentioned that this inequality signs here, they're not strict. Means that there is no d-dimensional body K for which this value and this value will be achieved. So, this is obviously not a constant for ball. So we are somewhere in very different situation here. And as the title of the talk says, inequalities are sharp. What it means? It means that there exist two families of convex bodies say K delta and K delta prime, such that the limit when delta goes to 0, functional from K delta So it means I have a family of the convex bodies which approximate my constants, this functional of convex bodies, approximate this constants as good as I wish. So I can't choose anything better here or here. That is sharp in this sense. And now I would like to, of course, to give a proof, or I will maybe skip some details because proof is quite long, but I will give the main idea of what is happening. And at the very end, I will also, I hope I will still have time to explain how we construct these families of bodies. So, and I would like to start by considering this functional delta of K. So I recall you that this is expectation of the length of this interval with a starting point x1 and endpoint x2, let's say so. And I already mentioned that this V1, this constant is chosen in such a way that V1 of intervals, this first intrinsic volume of interval, is just its length. So I have a length of the interval here. I can rewrite it in this way. So this is V1, the first intrinsic volume of the interval with a, let's say, starting point x1 and endpoint x2. And now I will use, oh, sorry, this is no constant. That's a mistake here. No constant. So it's just V1. And now I would like to use this formula for V1. This together with this basically, and rewrite what I have here. And so I can continue. It's a constant alpha D now appearing here. And then I already use Fubini theorem in order to exchange this integral over the unit sphere and expectation. And here I have projection of point x1 minus projection of point x2. So then du. Okay, so I can rewrite my function in this form. Let us now fix u and consider what happens when this expectation for fixed u. Well, I will just use the definition and rewrite this expectation as an integral. Dx1, dx2. And as the next step, I would like to introduce some change of variable, which I prefer to explain you all the picture. So this is what we need, I think. Let us consider the situation now. So we have some unit vector, and we have this line, which is the linear span of this unit vector. Then I can also consider this orthogonal complement of u. This is u perp. This is hyperplane. And so I have my points, x1 and x2, and I project them onto this linear span of vector u. And I would like to go from this standard orthogonal basis to the basis where this first orthogonal vector goes to u, and the rest is some orthogonal basis of u perp. So why I will benefit from this? Yeah, well, because now I can, for example, write what is this projection. I can write it like T1 u, and this projection I can write like T2 u. So here I will already benefit because I will just have T1 and T2 here. And then, so this hyperplane is u T1 u plus u perp, and this one is T2 u plus u perp. And then how much my first coordinates is T. T1 and T2 can vary. Okay, it can vary up to here. And this point can be written like supremum over all x in K, and then scalar product of x and u. And I will denote it by, so it's supremum, I will denote it by bu of K. And this point is also, this is infimum now, over all x in K, x, u. And I will denote it by a u of K. Okay, so this is my new coordinates. And now I can already notice that this guy here does not depend on, doesn't matter whatever happens on this u perp. So it doesn't matter on which exactly place of u perp this orthogonal complement, these points x1 and x2 are placed, they will be projected in the same point. It means that I can already integrate over this hyperplane, and okay, it's basically like I give a weight to this point, and this weight is exactly the volume of the intersection of my body K with this hyperplane. So it's exactly the weight each point here is getting. So, and now I will write it down. So I hope you got the idea. And also, so as I said, we do this change of variables, but that's basically rotation. So there is no Jacobian because it's just one. So I have from a u of K up to b u of K. Here I just have T1 minus T2. And here I have the volume. Volume, I mean d minus 1 dimensional volume of this K intersected with u T1 plus u perp. and here will be the volume of K intersected with T2 U plus U, or DT1, DT2. And I would also prefer to actually move this volume inside. So I would like to write it here. And those two guys already define some kind of, it's some function of T. So I will call it H tilde, depends on U, depends on K, T1. And that's exactly the same function, UK, depending on T2. It's already good, but I also don't like that there is something like this. So some numbers depending still on U and K, I don't like it. So I would like to rescale and introduce another change of variables when I actually shrink this integral or interval, or to transfer this interval to the interval -1, 1. So this is our change of variables. LU again, yeah, as I said, we map this interval into this interval, and the Jacobian is clearly this projection of body K to this linear span of U. So it's exactly the length of this interval here. And I would also like to introduce this function HT now without this tilde, and that is like rescaled version of H tilde after this change of variable LU. And so with all this notation, I can now write just directly, will follow from here, that I have here K multiplied by 1/2 integral from -1 to 1 to 1. So that's how it's written in very nice form. And so this functional, that is what I will work with now. And this is some functional depending on this function H, because this is what depends now on my body. And this is what I am interested in now. And also these functionals which are placed here, they are not arbitrary, they have some nice properties. And so I will describe now the class H of these functions, which can be can appear here. And okay, the first property is clear, that they have to be positive. Second as well, so they have support is this interval -1, 1. And so the next property is slightly less trivial, but still not that hard to verify, that this integral of this function is actually 1. So this is some probability distribution. It can be viewed as probability density function. And yeah, maybe how to verify it quickly. Just put 1 here and go back with all these computations and change of variables, and then we will just appear 1 here, because we will just integrate body K and divide again by the volume of body K square. So, and the last property is the most maybe important and interesting. This functional in power 1 over d minus k is concave. So this is a class of function I'm interested in. And so I can say now that any, oh, let's write it differently maybe. For any unit vector and any convex body K, this functional h u k of t, so that's the same like h of t, it belongs to this class. And this very last property D, it's actually just bronze concavity principle. Okay, so I basically moved my problem for convex bodies to the problem for some functional of functions. So, and my aim now to maximize and minimize this functional I of h for h from this class of functions. And so we now arrive to the most technical and let's say hardest or involved part of the proof. That's why I will just formulate it like main lemma. So for any this function from our class of functions, this functional is smaller or equals than 1/3 and bigger or equals than exactly this constant CD we also wish to obtain. And for the upper bound is attained even only if our function h is this indicator function of on the interval. And with the minimum, it's a bit more complicated. Minimum is attained even only if our function h is equal to h0, which has this form. So from this form, it's not clear why it should be minimized at all. But let us consider the function h in power 1 over d minus 1. And then this would be this is my h0 in power 1 over d minus 1. And we see that it's a linear function, that's a affine function. And for my class of functions, I need it to be concave. So it's like an extremal case. It's linear function is still concave, but if we go further, we might drop to convexity. So that's why this is a nice candidate for being a minimizer or maximizer. In this case, it appeared to be minimizer. So I will not give a proof of this lemma because, as I say, it's very technical. But now finishing the proof is very easy. So let us now recall. Delta of k was for us, it's some constant alpha d integral over unit sphere. And then I have this expectation of pu of x1 minus pu of x2. Sigma t minus 1 tu. And what I have here, we just also derived this is pu of k multiplied by the length of this projection of k onto the u multiplied by this functional. Okay, and then from here we directly see that then delta of k is smaller or equal than 1/3. And what stays here? Alpha d integral minus 1. This quantity. And this is exactly the first intrinsic volume of the body K. So great. And the same holds with the lower bound. So that's how we prove this non-strict upper and lower bound. But it's actually what we did. We also proved the strict lower bound. I will formulate it like a small lemma because it should be almost obvious, but that there is no convex body which for almost all directions, in almost all directions, this functional is actually h0 of t. That's two strong conditions. So that's why this value and this value would never be achieved. And as I promised, the last minutes I will spend on considering these families k delta and k prime delta on arguments for sharpness of our estimates. So as I said, there are two families of convex bodies, k delta and k delta prime. which whose like functional of these bodies approximates the lower bound k delta as good as we want, and also upper bound k delta prime as good as we want. And k delta is E1 ED is the standard orthogonal basis of RD, and k delta then is the convex hull of of these vectors. Here you see the picture. This is in dimension 2 here, and this is in dimension 3. So it's basically like some triangle-like structure. And when delta goes to 0, we go to this getting very, very thin somehow. And k prime delta is just a box, also with the size delta. And again, when delta goes to 0, we just getting very, very thin and very close to the interval. And how to prove, so I just give a short verification that this for these families is indeed this limit. These limits are like they are. What we first can know that, let us consider the this lower limit first. I can already say, so from our theorem, we proved this bound, and that's for all bodies. So it doesn't matter which bodies we consider. That's why lim inf is already bigger or equal than CD in this case. And similarly, in this case, lim sup is already smaller or equal than 1/3. This just follows from theorem. So we just need to consider lim sup in this situation and lim inf in this situation. Another thing I would like to point out here, that the limit when delta goes to 0 of B1 of k delta is equal to the limit when delta goes to 0 of B1 of k delta prime, and that is actually 2. Because both these bodies are getting very, very close to this just this interval -1, 1, and for this this is 2, this is value. So now let's consider first k delta. So now I would like to consider lim sup. So I want the upper bound. So this delta of k delta small is a expectation of the distance between two random points in this body. So I have point x1 and x2 here. And I again project it in one specific direction, in E1. And I can write down that it's smaller or equal than expectation of projection into E1 of x1 minus projection into E2 x2 and plus delta. So it's like triangle inequalities what I have here. And so now I split. This is expectation of this projection into E1 x1, projection into E1 x2, and plus delta. And now if we just carefully take a look on this body itself, then this expectation is again like if I project it, every point gets some weight, and the weight which we get is exactly this profile somehow. And this is exactly how our functional H0 looks like. So that's why this expectation is actually this CD plus delta. And that's why we also have this lim sup smaller or equal than CD. Good, and then for the second functional, I need the lim infimum, and it's even easier because I just say k delta prime. It's again the expectation of these two guys, and I again project into the onto the first coordinate, and now I just write this bigger than expectation of projection, the length of projection of this interval onto the first coordinate. Yeah, and again, if I take a look here, so I have 2 points, x1 and x2 here, and I project them. And again, each point gets some weight, but every point gets the same weight. So, and I end up again in this kind of profile, and this is exactly what is H1 describing. That's why, again, I have here just 1/3. That's why also lim inf here k delta prime is smaller or equal than 1/3, or bigger or equal, sorry. Yeah. So and that basically finishes the proof of these extremal cases and sharpness of the bound. So sorry that it took slightly longer, and sorry for my problems with 10. And yeah, I'm looking forward to your questions.
Thank you very much, Anna, for the talk. Yeah, how about some questions?
Hi, I have a question. You said that simplex conjecture implies hyperplane conjecture. Can you say a little bit more about this?
Oh, yeah, to be honest, I'm not prepared to talk about this now. I was reading it quite a long time ago, but it's actually a very, very known connection, and there are some very nice overview about this. So if you're interested, I can send you a link about this, and that's very, very well written there. So,
okay,
I mean, that's probably not very complicated, but that's not a one sentence, I would say so. This connection.
Yeah, thank you. What about other questions?
May I ask one more question? You had this class H of functions, so which 1/d concave and satisfy conditions, and you had your functions, which are projection volumes of the projections. One is, you said H belongs to capital H. What about the other inclusion? Is true that they are actually all functions from H can be described as little ht for some convex body K and some vector U?
So that's about the only, of course, question is whether any concave function power d minus 1 is can describe the volume of these intersections of some bodies, and that's something which is inside this Brun's concavity principle. Of course, the function has to be also continuous, because otherwise it's just, yeah, but that's false for concavity. I think yes, but I'm not 100% sure.
Okay.
I am curious about this. So you mentioned Grom's result can be generalized to moments. So do you have any versions of these bounds when I now take them the distance to some power?
Again, sorry?
So what if I took the distance now to some power r? I guess now that the Fubini trick, right, this doesn't carry over.
Yeah, I think there will be more problems with this, with the powers of this the distances. Yeah, and but actually, if we go now through the proof, so yeah, we will have problem already here, because here we applied somehow that the length is the first intrinsic volume's length and the power is not. What one can do in principle, there are some formula of Kingman which helps to express exactly this length and power r as the integral over cross sections of average cross sections of the body. I could try to work with this, but that's a totally different. So this proof will break already here. So it will not go further. But with the powers, maybe one can have another way to do it. But so maybe one can apply this Kingman's formula, but I think it's more complicated.
Thank you.